that. So it's my pleasure to introduce Frank to the stand. Thanks very much.
Thank you, Andy. Appreciate it. Good evening, and thank you so much for coming out to hear about the potential to make energy out of thin air. I hope you permit me to frame the discussion a bit because I'd like to talk to you about how important it is that we do, in fact, create energy from the air. We certainly have put the detritus of creating energy into the air, and therefore we now have to find a way to take it out and recycle it. In Jefferson's original effort to write the Declaration of Independence, he does in fact speak of life, liberty, and happiness, but he also wants a commitment in the Declaration that assures that one generation will hand to the next generation in usufruct the land as they found it. That means that you hand the land over not despoiled by your activities, but exactly as you found it, so that the next generation, the generations thereafter, can enjoy it as you have. I guess the hard question we have today, given the news about climate and our growth, is how, in fact, can we hand over the land to the next generation and those that will follow in usufruct? And clearly the news is very tough. Just looking at yesterday's Week in Review, on page 9, below the fold, we have Massachusetts 36% below the Atlantic Ocean, well distant into the future, admittedly, but nonetheless, it's a scary prospect, and that's what you were greeted with yesterday morning. And above the fold, the story was even more grim, about a gentleman who took his life to protest the lack of action to address environmental risks that we face today. But within that article was a remarkable quote, and it was uttered by Winston Churchill. And excuse me for reading it, you can read it yourselves, but in casting up this dread balance sheet and contemplating our dangers with a disillusioned eye, I see great reason for intense vigilance and exertion, but none whatever for panic and despair. And Churchill uttered that line at the moment when France was about to fall. What the article doesn't address is the fall of Holland not long before, days before, and the occupation of Southeast Asia, the growing occupation of Southeast Asia by the Japanese. Why is that important? It's important because the United States got 90% of its rubber from Southeast Asia. And all of that Southeast Asian rubber production were from Dutch colonies. So suddenly, that rubber production dried up. What did we do? We created out of whole cloth 38 synthetic rubber plants. 38 synthetic rubber plants. In 1941, we created 8,000 tons of rubber in this country. By 1945, we were manufacturing 830,000 tons of synthetic rubber in this country. And that enabled us to stop the Nazis. I worked at one of those plants. In 1984 and 85, we made tires. We also did something else. We made additives for oils. The additive was a polymer, and the additive enabled the oil to maintain a consistent viscosity in high heat and very low temperatures. And that process was a catalyst process. And off the catalyst came an effluent, because the catalyst process, like all processes, was inefficient. The effluent had within it some vestige of the raw material, which was very valuable to us. what did we do? We froze it into a liquid, separated that effluent, purified the propylene that we wanted to reuse, and were able to be profitable because of that recovery and recapture process. In 2001, I met Dr. Klaus Lackner. He had been interviewed, and I heard the interview. In the interview, he said that we need to capture CO2 from the atmosphere. It is the detritus of the energy that we have burnt since we began burning energy. We need to recapture that and reuse it to create useful products, including energy. I called him up. He was a professor at Columbia. And I went to meet him. And I said, how are you going to do that? And he said, well, we've got this chemical sorbent, and we only have to heat it up to a couple of hundred degrees, which was an improvement off of 1652 degrees, which was previously what you had to heat a sorbent to get CO2 off of it. And he said, but we can improve on that. And that was important. Improving on that was crucial, because if you didn't, you spent as much carbon to get the carbon out of the atmosphere, and therefore you'd made no gain. So I signed up. I said, Klaus, this is fascinating, and we need to pursue it. And from that came my company, Infinitree. And now I'd like to tell you about what that DREAD balance sheet looks like. So there it is. A gentleman named Keeling began to take measurements of carbon, of CO2 concentrations in the atmosphere in Hawaii in the late 50s. And this is what the progression shows. If you've seen Al Gore's first movie, you saw him describe this and explain what's ahead. So it is, in fact, a DREAD balance sheet, but is it completely? Is it completely? That line goes up, but then it comes down, that red line. And then it comes down again the next year. It comes down in each year, as a matter of fact. What's happening there? What's happening when that line comes down? What's happening is summer. What's happening is summertime. And plants are eating CO2 and releasing oxygen. Plants, by themselves, while we fly to California, while we drive to work, while we make steel, plants themselves are, in fact, reducing atmospheric concentrations. There's our hope. There's our hope. We have the opportunity to harness that potential, to take plants, feed them concentrated CO2, and they'll do the work for us. So that's what this talk's really about, and thank you for permitting me to frame it. Can we, in fact, harness plants to change climate? Can we, in fact, harness plants to create energy? Well, there is historical precedent for this, and this is, in fact, Earth. It's Earth 49 million years ago during the Eocene. And as you can see, the continents are largely arrayed around the roof of the planet, enclosing what is today where the Arctic Sea sits. And that phenomenon created an opportunity for plants to grow in that enclosed sea. How was it that they were able to grow on the Arctic Sea? Well, it was a vastly different planet. CO2 concentrations were probably 3,000 parts per million or higher. Temperatures, 72 degrees in the water up there. Crocodiles lived in it, in the Arctic. So it was a vastly different place. And in fact, because of that, and there's so much moisture in the air, it rained a lot. And it was, in fact, a receptacle for river water. And what happened was aquatic plants flourished. They flourished because they evolved in that high CO2 environment and consumed CO2 to their heart's content. And what happened over the course of 800,000 years was that those plants change climate. These aquatic plants change climate. And that event is called the Isola event. It is an event that we will return to, that Rob will return to in his talk. But it gives us considerable hope, because what did happen is that CO2 concentrations likely came down to as low as 800 parts per million, so just a little less than twice what they are today. And it began the possibility of an icehouse planet, a planet where we can in fact have glaciers, which was not the case 49 million years ago. So it changed the climate. So how does that help us, given what our needs are going to be energy-wise for the foreseeable future? Well, let's not focus on the foreseeable future. Let's focus on the next 25 years or so. It's pretty scary. What's being projected by people who would know is a requirement for energy security given populations that are becoming wealthy, giving our own voracious need for energy. We're predicting that in the next 25 years or so, we're going to require 80% of everything we've burned to date on the planet. 80% of everything we've burned to date. Well, that's a lot of oil. That's a lot of gas. That's a lot of coal. And if that were to all come from fossil fuels, well, atmospheric concentrations would rise in lockstep. And I think it's safe to say that we would have a climate catastrophe. So our business is to consider an alternative means of achieving energy security. So I ask you to engage with me in a thought exercise. So we have a cubic meter of air. And let's just say we're going to capture that cubic meter of air in a windmill. And let's just say for purposes of today that that cubic meter of air is moving at a rapid clip of about 22.5 miles an hour. So it's fairly windy. So we capture that cubic meter of air in a windmill, and we create 58 joules of energy. Pretty good, 58 joules of energy. So we've done something. Now let's take a look at that cubic meter of air from a different perspective. Let's just say that that cubic meter of air it has CO2 in it that was in fact created by the burning of gasoline. And let's just say it was created by the burning of Esso gasoline in 1964. You remember Esso. So that was burned by my parents as they drove me off to get a pizza in 1964. And the energy created by that burning, by the CO2 in that cubic meter of air, amounts to 10 kilojoules. So 170 times the amount of energy that we could grab from that cubic meter if we caught it with a windmill. So think about that. We have the possibility of creating legacy CO2 and utilizing it to create new energy for the future by feeding it to plants. Now, given what we just saw in terms of our energetic needs for the next 25 years or so, I think we have to capture that CO2 from that cubic meter of air and do it over and over and over again and try to create energy from plants in a carbon neutral manner. Our technology has been long in development. I started working on my company in 2011, and what we've tried to do was to create an efficient, low-energy means of capturing CO2 from the atmosphere. Now, that's hard to do. When you capture anything on a sorbent, it takes energy to break the bonds. You all remember 10th grade chemistry, and you remember that breaking a covalent bond requires a lot of energy, whether it's high heat, whether it's pulling a vacuum. It's not easy to do. So what we discovered was remarkable and gave us hope that we could feed greenhouses, vertical farms with cheap, low-energy CO2 with an enviable carbon footprint. So what we use is moisture, which is available in abundance inside of a greenhouse. We use moisture. The moisture alone is sufficient to release the CO2 from our sorbents. And what we've done is, in fact, pursue a path since that discovery of the moisture swing, the humidity swing, of attempting to explore other materials, other sorbents that capture CO2 very efficiently and can do so over and over and over again, so this process is of low cost. We also need to do it quickly, because the more cycles that we can do in a day, the less sorbent we need, the smaller the system has to be, and the cheaper it can be for the cultivator. So that has been our lengthy process, is to spend time to optimize the sorbents that we're using and to optimize the contact with the air, to change the geometry of the sorbent, and to make sure that we're getting the most CO2 for the energy we're spending. So this discovery is something that gives us great hope, and it's something that's gotten us some attention. We are, in fact, finalists in the Virgin Earth Challenge. 10,000 applications, 11 finalists. It's an important challenge. Richard Branson made it, and he made it some time ago, and he made it to inspire entrepreneurs to go out and try and find ways to capture a lot of carbon. In fact, he put a number on it, put a gigaton a year away. And I think they've softened that a bit, because a gigaton is a lot of CO2. It's a lot of carbon. But that was the ambition. And he did, in fact, inspire a lot of investment, a lot of work to try and create that outcome. We've been hard at it for some time, and I think that it's been a very fruitful process for us. And we've recently, with some frequency, have to update what our thinking is about how we will, in fact, put away a lot of CO2. So our eventual submission will represent not just applications like creation of fuel or plastics or aiding in the cultivation of tomatoes or lettuce, but it will also have, and has, a sequestration strategy. And what you see here is just that. So that is a farm that's not ours, but it is one that we would utilize as a model for a farm for the plant that Rob will now talk about. The reason we would use that plant is because it so voraciously consumes CO2 that for us to grow it in layers, 25 layers per our design, so you've got a vertical farm of 25 growth layers, would enable us to put away a lot of CO2. And you may have read, to go back to the New York Times, you may have read over the weekend about the potential of soil sequestration. That's our solution. So our solution has a number of steps, and I won't go into it in depth because we want to get to Rob's discussion. But the key point is that of all of the carbon sinks on the planet, soil is the one that is the most vast. Unlike the ocean, it hasn't acidified, and in fact wants the CO2. We have used CO2 to make the corn in the American Midwest, and that soil wants CO2 back. So that's our strategy, and I would urge you actually to go and look up the article in the Weekend Times magazine, because it really states what the objective is very clearly, and that's part of our strategy. So we hope to put away gigatons of CO2 in soil, and that picture is, in fact, part of our system. We are, all of us, changing the earth. We do so in an infinitesimal way, independently, but together we make quite a big difference. And that's something that should cause us to step back and take note. The fact is that the gentleman, you remember years ago we had a challenge on the planet about what to do with ozone depletion. It looked like an Earth-ending or a human-ending problem, and it is if it's not addressed. The Nobelists who did the work on ozone-depleting chemicals in the atmosphere, Crutzen, has since suggested that the time that we're living in, the epoch, should be named after us. Should be named after us because what will come from here, how the Earth will evolve from here, is dependent on our activities. Now that's something to consider. So what we're hoping to do is to turn back the clock a bit and to create at massive scale an ability to draw down CO2, put it in plants which wants it anyway, and put it in soil which also wants it.